Breakthrough Projects. In this video, we are going to explain about the project entitled as Securing Networks Against Adversarial Domain Name System Tunneling Attacks Using Hybrid Neural Networks. So, before getting into the video, let me give you the brief description about the project. This work focuses on protecting computer networks from DNS tunneling attacks, where attackers secretly transmit data to DNS requests. It proposes a defense method using a hybrid neural network model that combines multiple deep learning techniques to accurately detect and block these hidden malicious communication channels. Coming to the abstract states that DNS tunneling attacks pose a significant threat to modern network security by allowing attackers to secretly bypass defense and exfiltrate data through schemingly legitimate DNS traffic. Traditional detection methods including signature-based approach, statistical analysis, and classical machine learning often fails to identify sophisticated or evolving attacks because they cannot capture the complex pattern hidden within DNS queries. To address these limitations, this research introduced a hybrid neural network approach that combines convolutional neural networks for automated deep feature extraction with long short-term memory networks for analyzing the sequential and temporal behavior of DNS traffic. This integrated model enhances detection accuracy, minimize false positives, and provide a more adaptive and intelligent mechanism for identifying both known and emerging DNS tunnel attacks, offering a more robust solution for securing network environments. Coming to the existing system states that detecting DNS tunneling attacks mainly rely on signature-based, statistical, and traditional machine learning models, but each has significant limitations. Signature-based systems only detect known attack patterns and fail against new threats. Statistical approaches analyze features like query length, entropy, or frequency, but often misclassify legitimate high-volume traffic as malicious, leading to high false positives. Traditional machine learning models depends on manually engineered features and struggles to capture the sequential or temporal nature of DNS queries, making them less effective against evolving adversarial techniques. Overall, these existing methods provide limited and unreliable protection against sophisticated DNS tunneling attacks. Coming to the proposed system or base paper work. The proposed system overcomes the limitations of existing DNS tunneling detection methods by utilizing a hybrid neural network that combines convolutional neural network with long short-term memory networks for enhanced accuracy and adaptability. CNNs automatically extract deep and complex features from DNS queries, eliminating the need for manual features engineering and enabling the detection of subtle anomalies that traditional approaches often miss. LSTM networks then analyze the sequential and temporal patterns in DNS traffic, capturing how attacks evolve over time and identify malicious behavior spread across multiple queries. By integrating these two models, the system can more effectively distinguish between legitimate and malicious DNS activity, reduce false positives, and adapt to new or evolving attack strategies. This hybrid architecture provides a more intelligent, precise, and resilient solutions for detecting sophisticated DNS tunnel attacks compared to convolutional detection techniques. Coming to the dataset, the adversarial machine learning dataset on Kaggle is designed to support research on detecting and defending against adversarial attacks by providing both benign inputs and intentionally manipulated samples meant to devise machine learning models. However, the dataset lacks detailed documentation, offering no clear description of its structure, attributes, feature types, or number of samples, and it does not include a formal data dictionary. As adversarial datasets typically contains clean and perturbed inputs generated through various attack techniques, it is likely that this dataset follows a similar format possible stored in CSV files or image-based structures compatible with standard machine learning pipelines. Due to the absence of metadata, users must thoroughly inspect and pre-process the dataset, checking for missing values, understanding the feature distributions, interpreting labels, and identifying potential inconsistent or biased. Despite these challenges, the dataset remains valuable for preliminary experiments in adversarial detection and robustness testing. Two researchers aiming for formal publication grade work should pair it with more well documented data sets to ensure reproducibility and reliable evaluation. Coming to the novelty or extension or enhancement or improvement. This project includes several important extensions that enhance both model performance and usability. Firstly, additional machine learning models such as XGBoost, a hybrid XGBoost model, and a stacking classifier were developed to compare with the primary system. Among this, the stacking model combines predictions from multiple Bayes learners, achieved the highest accuracy of 92.7%, demonstrating superior predictivity capability. To improve the interpretability, explainable AI techniques such as line and sharp were incorporated, allowing users to understand how individual feature values influence model decisions and providing transparency behind each prediction. Furthermore, a user-friendly interface was developed using the Flask framework, enabling users to input data directly through a web-based UI and receive predictions from the trained models, making the system more accessible and practical for real-world use. Coming to the flow of the work, firstly, we need to import the packages. All the required Python libraries and frameworks are imported, including tools for data handling, pre-processing, visualization, machine learning, deep learning, model evaluation, and explainable AI. This step ensures that all functionalities needed throughout the project are available. Next, exploring the data set. The adversarial machine learning dataset from Kaggle is loaded and examined. Since the dataset is split into multiple class files, all class-wise datasets are combined into a single unified dataset using pandas to create a complete view for analysis and modeling. Next, data pre-processing. Pre-processing includes cleaning the dataset by removing null values and duplicate entries to ensure consistency and quality. This step prepares the raw data for reliable training and modeling. Next, we have mapping target classes. All target labels, originally in string format, are converted into integer values. This mapping is essential because machine learning models typically require numerical labels for classification tasks. Next, we have resampling the data. To address the class imbalance, SMART is applied. This ensures that the dataset has balanced classes representation, preventing models from being biased towards majority classes. Next, we have normalization. Feature values are normalized using standard scalar so that all variables follow a similar scale. This improves model training, stability, and ensures that no feature dominates due to larger numerical ranges. Next, we have data visualization. Visualizations such as classification distribution plots and correlation matrix are generated. This helps in understanding feature relationships, dataset imbalance, and underlying data patterns before modeling. Next, building the classification models. Multiple machine learning models like random forest, decision tree, gradient boost, KNN, and logistic regression are trained using X-train and Y-train. Predictions are obtained for both training and testing sets. These models use the baseline for performance comparison. Next, we have training the models. The model is trained using the prepared dataset, allowing it to learn patterns and relationship between features and target variables. Optimization techniques adjust the model's parameters so it can make accurate predictions. Next, comparing the models. Each trained model is evaluated using the metrics like accuracy, precision, recall, F1 score, and ROC AUC. These metrics help measure how well the model performs and identify which one is most reliable. Next, we have comparison graphs. Graphs such as bar plots, line charts, and ROC curves visually compare the performance scores of all models. These visuals make it easy to understand different and choose the best model. Next, we have save the best model. The model with the highest performance is selected and saved to a file so it can be reused later without retraining. This enables easy deployment and consistent predictions. Next, we have explainable AI techniques like LIME and SHAP. LIME and SHAP are used to interpret the model's prediction by showing how each feature influences the output. This explanation helps build trust and provide insights into the model's decision making. Next, we have the front-end deployment. A user-friendly interface is built using Flask, including registration and login functionality supported by an SQL database for secure user management. User can enter feature values on the web interface. This input represents the features required by the trained model for prediction. The input values provided by the user are pre-processed using the same transformations applied during model training to ensure the consistency. The saved trained model is loaded and the pre-processed user inputs is passed to the model to generate predictions about whether the input corresponding to begin or adversarial activity. The final prediction is displayed to the user in a clear and understandable format through the front-end interface, completing the workflow from input to the output. The algorithms used are ML models. We have used random forest, decision tree, gradient boost, KNN, and logistic regression. The hybrid models which we used are random forest with hybrid model, decision tree with hybrid model, gradient boost with hybrid model, KNN with hybrid model, and logistic regression with hybrid model. As an extension, we have used XGBoost and XGBoost with hybrid model. Along with that, we use the stacking classifier. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to deploy, test, and develop your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files, which contains algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file with the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax error or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is the front end built using Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Now, click on sign up so that all the given details are stored in signup.db and the login HTML will be opened where you need to access the application by username and password. Then click on sign in. This is the prediction page that has been displayed. In this we have detection button, graphical analysis button, notebook button and sign out button. So firstly click on detection button so that the predict attack form will be opened where you need to enter the input values and predict the attack. As we have three attack types, that is CW, FGSM and JSMA and legitimate, which means no attack. Let us check the attacks by giving the input values. First, MDT value is 33.7.3298. MA value is 617.6011. MQ value will be 147.4073. VDT value is 397.3879. VA value will be 3294.8.89. VQ value will be 397.3879. SDT value will be 397.3879. SA value will be 337.3298. SQ value will be 337.3298. KDT value will be 4060.933. KA value will be 337.3298. KQ value will be 2999.907 and ground truth will be 1. Now click on predict so that the input values are pre-processed and the output is displayed as CW. The predicted attack is CW and the confidence level is 99%, and we also have some attack information and recommendations like attack causes, safety measures and related information. And we also have analyze another query. By clicking this, we get the prediction form where we can give the inputs to predict other attacks. So the MDT value will be 2.649329. MA value will be 258.529. MQ value will be 88.3704. VDT value will be 25991.83. VA value will be 35950.37. VQ value will be 1297.226. SGT value will be 70.66463. SA value will be 2.064281. SQ value will be 37.21558 and KDT value will be 4992.658. KA value will be 4.664802. KQ value will be 2000556 and the ground truth value is 0. Now click on predict button so that the input values are pre-processed and the output is displayed as legitimate, which means it doesn't have any attack. The confidence is 55%. And we also have that attack information and recommendations like the attack cause, safety measures, related information. Now click on Analyze Another Query and let us give the input values. MDT value will be 1.77355. MA value will be 259.844. MQ value will be 88.379. VDT value will be 11178.4. VA value will be 34390.01. VQ value will be 473.926. SDT value will be 70.28504. SA value will be 1.690973. SQ value will be 55.79406. KDT value will be 4984.843. KA value will be 3.578368. KQ value will be 2771724. And the ground truth value will be 0. Now click on predict so that the input values are pre-processed and the output is displayed as FGSM attack. The confidence level is 99% and we also have the attack information and recommendations like attack costs, safety measures and related information. And click on Analyze Other Query. And let us give the inputs. Like MDT value will be 0.486089. MA value will be 314.164. MQ value will be 88.292. VDT value will be 82.20821. VA value will be 31768.66. VQ value will be 1689.68. SDT value will be 62.82502. SA value will be 1.569535. SQ value will be 33.38092. KDT value will be 4291.342. KA value will be 269559. KQ value will be 7.07571. Ground truth value will be 1. Now click on predict so that the input values are pre-processed and the output is displayed as JSMA attack. The confidence level is 99% and we also have the attack information and recommendations like attack costs, safety measures and related information. Now click on graphical analysis. Graphical analysis is a process of presenting the data in graphical formats like charts, plots, or images to easily understand the patterns, distributions, and relationships. So first we have sample outcomes graph. The pie chart displays the proportional distribution of 4 categories: legitimate, JSMA, FGSM, and CW. Each slice represents how much of the total data set falls into that category. The percentages are all very close to one another, around 25% each, with legitimate samples make up to 24.9%, JSMA at 25.2%, FGSM at 25.2% and CW at 24.7%. This near equal distribution suggests that the dataset is balanced across these four classes. The label indicates that JSMA, FGSM, and CW are likely adversarial attack types, while legitimate refers to non-adversarial data. The purposes of that chart appears to be showing that no single category dominates the dataset, ensuring fairness or uniformity in whatever analysis or model training the data is used for. Next, we have balanced sample outcomes graph. The pie chart illustrates an evenly distributed dataset across four categories: legitimate, JSMA, FGSM, and CW. Each slice occupies exactly 25% of the chart, showing that all categories contains the same number of samples. This perfect balance indicates that no single class dominates the dataset, which is especially important in machine learning tasks where equal representations helps prevent model bias. The label suggests that JSMA, FGSM, and CW refers to different adversarial attack methods, while legitimate represents normal, unaltered data. Overall, the chart emphasizes that the dataset has been intentionally structured to ensure fairness and equal weighting across all four sample types. Next, we have correlation matrix graph. This correlation matrix heat map illustrates how strongly different statistical attributes relate to one another, with color ranging from cool tones for weak or negative correlations to warm tones for strong positive ones. The attributes include MDT, MQ, SDT, SA, SQ, KA, VDT, VA, and KDT. The heat map reveals that several attributes, particularly the mean, standard deviation, and kurtosis measures, are highly correlated, shown by the deep red cells indicating strong linear relationship among them. In contrast, attributes like variance-related measures exhibit weaker correlations, reflected by cooler colors. Overall, the graph provides a compact visual summary of how these statistical features interact, helping identify strongly related variables and potential redundancy within the dataset. Next, we have confusion matrix graph. The confusion matrix visualizes the performance of the stacking classifier across four classes: legitimate, CW, FGSM, and JSMA. Each cell shows how many samples of a true class were predicted in each label. The strong diagonal values, such as 554 for legitimate, 503 for CW, 558 for FGSM, and 581 for JSME, indicates that the model correctly classified most samples in each category. Misclassifications are relatively low, with some legitimate samples predicted as CW and some CW samples predicted as legitimate, while FGSM and JSMA classes shows almost no confusion with others. Overall, the metrics demonstrate that the classifier performs very well, accurately distinguish between normal samples and different types of adversarial attacks with minimal error. Next, we have accuracy graph. The bar chart compares the performance of various machine learning models, both standard and hybrid versions, based on their accuracy scores. Each bar represents a different model, showing how effectively it predicts the correct class labels, while most models achieve reasonably high accuracy. The stacking model clearly outperforms all others, reaching the highest accuracy among the set. Models like XGBoost and its hybrid version also performs very well, whereas models such as logistic regression and LR hybrid shows comparatively low accuracy. Overall, the graph highlights that ensemble-based methods, particularly stacking, delivers superior performance in this analysis. Next, we have precision graph. The bar chart compares the precision score of various machine learning models, including both standard and hybrid versions. Precision measures how many of the model's positive predictions are exactly correct, making it especially important when misclassifications carry significant risk. The graph shows that while most models achieve high precision, ensemble-based methods outperform the rest, with stacking achieving the highest precision overall, followed closely by XGBoost and its hybrid versions. Models such as logistic regression and its hybrid form demonstrate comparatively low precision. Overall, the chart highlights that advanced ensemble techniques provide the most reliable and accurate positive predictions in this evaluation. Next, we have recall graph. This bar chart shows how effectively different machine learning models identify all relevant positive cases. A crucial metric when missing true positives can be costly. The results indicate that while most models achieve reasonably strong recall, the ensemble-based approach again stands out, with stacking achieving the highest recall, followed closely by XGBoost and its hybrid variant. Models like logistic regression and its hybrid from exhibit comparatively low recall, meaning they miss more true positives. Overall, the graph demonstrates that advanced ensemble models consistently deliver better sensitivity, making them more reliable for tasks where detecting every positive instant is essential. Next, we have F1 score graph. The bar chart compares the F1 scores of various machine learning models, highlighting how well each model balances both precision and recall. The result shows that while most models perform reasonably well, the ensemble-based methods once again lead in effectiveness, with stacking achieving the highest F1 score, followed closely by XGBoost and its hybrid variant. Models like logistic regression and its hybrid versions score lower, indicating weaker overall balance between correctly identifying positive cases and avoiding false positive. Overall, the graph demonstrates that advanced ensemble approaches provide the most robust and reliable performance when considering both precision and recall together. Next, we have ROC-AUC graph. The bar chart compares the ROC-AUC scores of various machine learning models, showing how well each model distinguishes between classes. Overall, nearly all models perform strongly with ROC-AUC values clustered between roughly 0.85 and 0.98. Simpler models like logistic regression and KNN have slightly lower scores, while ensemble and hybrid models such as gradient boost, XGBoost, random forest variants, and especially the stacking model achieves the highest performance. This suggests that combining models or using more complex ensemble methods lead to better classification capability in this task. Next, we have SHAP value graph. This SHAP summary plot shows how each feature influences the model's prediction, with points representing individual samples and color indicating whether the feature value is high or low. Features at the top, such as MDT and MA and SA, have the greatest impact on the model output, meaning they contribute most to predict the target. Positive SHAP values push prediction towards the positive classes, while negative values push them towards the opposite. The spread of points along the x-axis indicates how strongly each feature affects different predictions, and the mix of colors shows whether high or low feature values tend to increase or decrease the model's output. Then click on sign out. So finally, this project demonstrates that hybrid neural network models significantly enhance the detection of mitigation of adversarial DNS tunneling attacks, outperforming traditional security techniques. By combining deep learning architectures with behavioral network analysis, the system provides robust adaptive defense against convert data exfiltration. The approach strengthens overall network security resilience and offers a scalable framework for future threat detection advancements. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.